All right, what's up, everybody? All right, so welcome to the next video here. Little slight change in plans in terms of our schedule for the next 2 weeks. I was thinking about things and looking at the upcoming content, and for the most part, it's still going to be the same, just a slight change from what I talked about last week. So I wanted to show you exactly what I mean by that. So here's the calendar for the remainder of November and the beginning part of December. I'm actually going to go through pretty much the remainder of the year right now. So today is the 22nd. Okay. What you're going to be doing today is looking at the 3.6 content, actually. This actually ties more closely to 3.4 than it does to 3.5, which is a little bit weird. So we're going to go slightly out of order. And the good news about this is that it's a nice and short, simple topic. You're not even going to have an assignment for me. I did a little bit of thinking, and over Thanksgiving break, I don't want to give you guys anything to do, okay? Because I'm certainly going to be taking some time off to just kind of relax and sort of catch up on some stuff that I need to catch up on. So I'm not going to be giving you all a new assignment to work on over Thanksgiving break. I want you to, be able to relax and spend some time with your family, kind of recharge your batteries a little bit, like I will be doing. There will be a video over Thanksgiving break. I'm probably not going to have this ready until Saturday or Sunday, okay? That will be over 3.5, okay? And that is, that will be sort of the last bit of new content that's going to be on the assessment, the summative, which will be that Friday. I know that puts us in a little bit of a time crunch. So what we're going to do is, I'm going to keep the assignment relatively simple. We're going to try to go over things on that Wednesday, and then I'll have that sort of optional study session on Thursday. Okay, so just to go over that one more time. Short video today on 3.6, no new assignment. There will be another video posted over Thanksgiving break for you to watch on 3.5. We'll work on some problems related to that on Tuesday. We'll sort of go over everything on Wednesday, and then I'll have my optional study session after school on Thursday in preparation for our summative on Friday. Okay, and then that leaves us with 2 full weeks remaining in the semester. I don't anticipate there being another assessment, okay? So after this one on Friday, we're just going to have 2 weeks here. Technically, we're not supposed to do any sort of new content during this last week, but they have told us that if you're doing AP or dual credit classes, that's a little bit flexible. So we are going to continue doing some new content, but there's not going to be an assessment or anything, okay? So yeah, we'll just have sort of 2 weeks to continue moving through Unit 3. I think we can probably wrap up Unit 3 in this time, okay, or mostly wrap it up. And then we'll do some sort of assessment after Christmas break, okay? Okay, so let's get into the actual notes for today. Like I said, this is 3.6, not 3.5, so we're going to be going a little bit out of order, which is totally okay, not a big deal. I'm not sure why this is, I don't know why they ordered it like this, but anyways. Topic 6 is on deviation from the ideal gas law. So, and you'll see here with the objective and the essential knowledge here, really short section, right? We need to explain the relationship among non-ideal behaviors of gases, inner particle forces, and or volumes. So we're just going to be talking a little bit more in depth about, what makes an ideal gas, what makes a gas act ideally, what can make it act non-ideally, and it's going to be a quick video, okay? And like I said, I'm not going to have any sort of special, I'm not going to have a new assignment for you on this because, the types of questions you'll be asked, if any, about this on the AP exam are going to be qualitative in nature. And so I don't really think it's worth doing a whole big assignment over Thanksgiving break for what really is a relatively simple concept. So just going to have 2 topics. We're going to talk about what it means to be ideal again. This is a little bit of review from last time. And then we're going to talk about the deviation conditions and what those mean. So like I mentioned in the 3.4 video, no real gas is perfectly ideal. Okay, a true ideal gas is a gas whose particles take up no space, so the particles themselves have no volume, which can't be true, obviously, and those particles have no interparticle interactions, no IMFs. That is also impossible. Okay, you're always going to have the potential for some dispersion forces. Okay, and some gas particles may be polar, in which case those interparticle interactions may be more substantial than dispersion forces. Right, you could have some actual dipole forces present as well. So the conditions that lead to the most ideal conditions are low pressures and high temperatures. Okay, and we're going to look at those in some more detail right now. So here's what I'm trying to do here in the next couple of slides is show you sort of ideal versus non-ideal, okay, and talk about why that is, okay, because what you really need to understand, at least for the AP exam, is if you're reading through a scenario and they ask you something about ideal versus non-ideal behavior, you really just need to be able to recognize, okay, what situations are going to be ideal, what situations are going to be non-ideal. So the first distinction is this distinction between low and high pressure. Okay, so these are two scenarios here. The image here on the left is a low pressure scenario. The image over here on the right is a high pressure scenario. The reason that this over here on the left is a more ideal scenario, two reasons. Okay, so this is more ideal for two reasons. Reason number one, okay, so let's say you have the same number of particles, right, in both spots here. The amount of space that these particles take up compared to the overall volume is relatively small. So how can I write this? Volume of particles per total volume, this ratio, okay, is really small in ideal conditions, okay? Right, because your particles are nice and spread out, they've got lots of room in between them, and so these particles are going to be pretty small, right? This is certainly not to scale. Usually individual molecules or individual atoms are really small compared to the chambers that they're held in. So, but anyways, the what I was saying before, the volume of the total volume of the particles divided by the total volume of the container, this ratio is going to be pretty small. On the right hand side though, okay, so this ratio is small over here. It's going to be large, or at least larger on the right hand side. The total volume of the particles when compared to the total volume of the container, a little bit more substantial, right? And so once again, this is not exactly to scale, but I think you get what I'm saying, right? The more tightly those particles are confined, the higher the pressure, the more condensed the gas is, the larger this ratio is going to be, okay? So that's one reason. The second reason, which kind of, it doesn't, not completely unrelated to number one here. If these particles are, in a low pressure scenario, meaning that they are sort of more spread out and have, more room to move around, the likelihood that they run into each other is lower than if they are closely condensed with each other, right? So how can I phrase this? Likelihood, oh man, I'm not sure I know how to spell this word. Hold on a second. Let me try this again. Okay. I think I'm misspelling this word, likelihood, of interparticle interactions, I should say. The likelihood of interparticle interactions is small in low pressure scenarios, and it's larger in high pressure scenarios, right? Because the particles are literally just more condensed, they're just closer together. They're going to collide with each other more often in a high pressure scenario versus a low pressure scenario, okay? So what you need to understand about ideal versus non-ideal conditions is that if you have two scenarios, one that's low pressure, one that's high pressure, the one that's low pressure is going to act more ideally than the one in high pressure, and that is due to these two reasons. The particles in the low pressure scenario don't have much volume compared to the total volume of the container, and the likelihood of those particles having interactions with each other is smaller or lesser than over here in this scenario because they're just more spread out. Okay? All right, let's look at the other sort of deviation condition, and that is temperature. Okay? So once again, the ideal scenario here is high temperature, non-ideal is low temperature. Why? Well, this really boils down to one reason, okay? And it has to do with what temperature is, okay? So remember, I've talked about this a few times, and 3.5 is going to talk much more about this, okay? Temperature is defined as basically a measure of the kinetic energy of particles. It's closely related to their speed. Okay, that's really what temperature is. Okay, particularly of a gas. Okay, temperature is just sort of a measure of the speed of the particles. If you have a high temperature scenario, the particles are moving faster than in a low temperature scenario, and that's represented by the lengths of these arrows. Okay, in a high temperature scenario, if two particles collide with one another, they are colliding at a higher speed, and there's more energy involved. There's more kinetic energy involved. They are less likely to be. They're less likely for any interparticle interactions to affect them if they are moving at higher velocities. Okay, so let's just take I don't know. Let's take none of these particles look like they're actually running into each other. Here, we'll take these right here. Okay, so these two particles moving at high velocities because of that high temperature. If and when they run into each other, okay, let's say that they're polar molecules. Okay, let's say they're maybe it's water. Okay, H2O. Okay, so these are polar molecules. When they collide, they're going to have a propensity to stick to one another, right? Because they have the positive end, the negative end, right? And so that they're going to want to stick together. However, if those particles are at higher temperatures, meaning higher velocities, they have enough. They're going to have a better chance of actually just bouncing off one another, overcoming the attractive interactions of that dipole-dipole interaction if they're at high temperatures. Okay, so if they have high velocities, if and when they collide, they have a higher chance of sort of ignoring the interparticle interaction. Okay, if they're at low temperatures, if and when they collide, they have a higher likelihood of actually sort of sticking together and that intermolecular force of that interparticle interaction actually having some sort of effect. That's what you don't want, okay? In an ideal situation, right, what we said before was that in an ideal situation, particles have zero intermolecular interactions, right? That is going to be more closely observed in high temperature situations than in low temperature situations, okay? So, what can I say here? Sort of what you're looking for, or what you want to be thinking of, is in high temperatures, IMFs have less impact due to high kinetic energy, right? And so when particles collide, the fact that they both have so much kinetic energy, that enables them to sort of escape the effect of that intermolecular force or that interparticle interaction, whereas in a low temperature situation, they can't necessarily do that, okay? They don't have enough energy to sort of escape. If they collide and they would bounce off each other, maybe the positive and negative charge are able to sort of hold those together. And that's really what causes gases to behave non-ideally, okay? I think this is nicely summarized in the next picture here, ideal versus real. Like I mentioned before, sorry about that. My computer's been asking me to restart like twice a day. Okay, in ideal conditions, you have high temperature, low pressure, so your particles are nice and spread out, right? Moving quickly. Particle size is small compared to the space between particles, or compared to the overall volume. And the interactions, really? And the interactions between particles are insignificant, okay? The non-ideal conditions are opposite of that. Low temperature, high pressure, lots of particles condensed in here. The particle size is significant compared to the space between particles, and the interactions between particles are significant, okay? And for all those reasons I sort of, clumsily got through in the last two slides, that's why, okay? And you can kind of see why you're not really going to have any sort of calculations or anything to do with this in this class. You actually can calculate sort of non-ideality. There are a few equations called like the van der Waals equation, for example, that can help you sort of estimate or approximate non-ideal gas behavior. But that is definitely beyond the scope of our course. That is something that you would get into in, say, like a college level thermodynamics course, or a physical chemistry course, or like even a chemical engineering course. Not something that we have to worry about is actually doing any sort of calculations. What you need to know is that ideal conditions are high temperature, low pressure. Non-ideal conditions are the opposite of that, and why those are non-ideal conditions, right? And that is because of the significant particle volume compared to the overall volume, and the fact that the interactions are going to be more significant than they would be in ideal situations. Okay, anyways, thanks for watching, and I will see you in class on Tuesday. We'll have a pretty quick class on Tuesday, and then we'll be ready to go for a Thanksgiving break. So hope you guys are looking forward to it, and I'll see you then.